Hi, I am Vaibhav Bedi and today we are going to discuss about aromaticity. Though in previous videos we have covered a lot of concepts about resonance, but this time we are going to discuss a very important topic, and a lot of questions are frequently asked in JEE and NEET and various other science-based examinations. So, uh, what is aromaticity? When we consider a benzene molecule, we always say that electrons move around the molecule in a loop. Okay, so when electron move, uh, then they create magnetic field, as we know in physics we have learned always. So this molecule has its own magnetic field, and when we put this under an external magnetic field, then this will react according to it. Either it will support or either it will oppose. So we are going to study that which are the compounds and how they oppose, and which are the compounds which support. Now there is a basic confusion that whether aromaticity is always with resonance. Yes, resonance is always there, but one more thing is that loop current must be formed, means there should be a closed path for an electron to move. If we consider this molecule, there is resonance, but a closed path for an electron is not there, means loop is not forming. Only one or the other way the electrons are moving. Okay, now there are some divisions which are based on reaction to external magnetic field. Now first is aromatic compounds. Now these are the compounds which supports the external magnetic field, which means that if we put them under external magnetic field, they will enhance the net magnetic field, which is due to the external plus their own magnetic field. Okay, now there are some conclusions which we can draw, that which are the possible molecules which can show aromatic, which can be aromatic compounds. Okay, now first is pure p molecules, means if a molecule is planar and it has perpendicular pure p, it may show aromatic compounds, it may be a aromatic compound. Second is incomplete octet. For example, look at this molecule. This is definitely aromatic compound, uh, because it has, if we see this molecule in a different angle, we can see that there are perpendicular pure p's and there is a pi bond. So the electrons can jump from one to each other, and from previous video we can easily remember that there must be a pi bond, then single bond, pi bond, and there is pure p as well. So this is definitely will show resonance, and further it will be aromatic. Now the third is delocalized lone pair. In this spiral we can easily see that nitrogen's lone pair is involved in resonance, and if it is involved in resonance, then it may be an aromatic compound. Okay, now next, delocalized negative charge. In this we can easily see that this negative charge will go inside and this pi bond will come outside and it will show resonance. Now it is showing resonance, there is a loop current as well, then it may show aromaticity, means it may be an aromatic compound, but it may be non-aromatic, it may be anti-aromatic as well, that we will find later in the video. Okay, now vacant d orbital. In this we can see that boron is, its octet is not complete, so nitrogen will provide the electrons, and this will simultaneously happen with three of the pairs. So it may show aromatic, it may be an aromatic compound. Now here the rule comes which will state that it is aromatic or anti-aromatic. So there is aromaticity, then there are two possibilities, one may be aromatic or second is anti-aromatic. So for a compound to be aromatic, it must follow this 4n plus 2 pi electron, means the electrons which are involved in resonance must be this type, means there may be 2 electrons, 6 electrons or 10 electrons, or further if we put any natural number in place of n. Okay, now for example in benzene we have three pi bonds which are involved in resonance. So each pi bond has two electrons, so three pi bonds will have six electrons, and six electrons is agreeable to this formula. So benzene is aromatic and it will support the external magnetic field. Now the our next topic is anti-aromaticity. Now what is anti-aromatic compounds? These are the compounds which will oppose the external magnetic field, which means when we will put these compounds into external magnetic field, the net effect of the magnetic field will be reduced. Now it will be reduced because it's the compound's own magnetic field will be opposite to the external magnetic field, so they will cancel out each other. Now for example, look at this. Now look at this. Uh, there is a rule for anti-aromaticity, that is 4n pi. Like we had for aromatic compounds, that must be 4n plus 2 pi electrons, but for anti-aromaticity we have 4n pi electrons. And for example, let's see this. We know that there is a pi bond, there is a negative charge, and the loop current will be there as a resonance is there, but the number of electrons which is participating in electron, that is 2 from here and 2 from here, so 4 electrons are there, so this will be anti-aromatic and it will oppose the external magnetic field. Now the next topic is non-aromatic. Now this is very simple. No loop current will be there, so the molecule's own magnetic field will vanish and there will be no effect on external magnetic field. Now if we consider the stability of these three type of compounds, the most stable is aromatic compound, then non-aromatic compound, and the least stable is anti-aromatic compound. So this is very simple to think that why it is so. Now for example, if we put aromatic compound in external magnetic field, so there is a magnetic field of own molecule in one way, suppose it is from north to south, okay, and we are putting external magnetic field in north to south direction as well, so it will support the molecule's own magnetic field, and the electrons will tend to move faster. So as they will move faster, they will lose more energy, and if more energy is extracted from the system, it is being more stable and more its potential energy is decreasing, so it is good for the molecule. Now here is a chart which sums up whatever we have done about these three molecules. Let us quickly revise it. So aromatic, anti-aromatic, non-aromatic, the structure must be planar for aromatic because loop current must be formed or resonance must be there. For anti-aromatic, resonance is also compulsory, so the structure should be planar, whereas for non-aromatic compounds the structure is non-planar, most of the times non-planar. Okay, so there must be pure P present in aromatic compounds. In anti-aromatic, because loop current must be formed, there must be pure P. For non-aromatic, there is no need. Loop current must be formed in aromatic compounds, loop current must be formed in aromatic compounds, but in non-aromatic compounds loop current does not formed. Now what is the rule? So there was Huckel rule for aromatic compounds, that is 4n plus 2 pi, 4n pi, and nothing for non-planar. Now let us move to some of the examples which will clear our concepts. Okay, now there is one trick or one tip or one hint which I can say, that whenever we want to find out different types of this resonating structure, that whether there will be aromatic or non-aromatic or anti-aromatic, always see number of electrons which take part in loop current. So resonance may be there in many parts of the molecule, but wherever the loop current is forming, that part will show aromaticity, and then we have to check whether it is aromatic or non-aromatic, anti-aromatic, sorry. Okay, now first one, we can see that resonance is there, but sorry, no loop current, so it will be non-aromatic. In second, of course there is loop current and resonance, but now we have to calculate that what number of how many number of electrons are there. So 2 2 2 2, so total 8 electrons are there, and that fits in the category of anti-aromatic according to the rule 4n pi. And if we put n equal to 2 in 4n pi, then we will get 8 electrons. Now third one is this structure. uh, Now we have to very cleverly see that this lone pair of nitrogen is not involved in resonance. So if it is not involved, we are not going to calculate in our rule. Means the rule which was for n plus 2 pi, in that we need not to calculate this nitrogen's lone pair. Okay, so there are 6 electrons which are jumping around, and this fits into the category of aromatic compounds according to the rule 4n plus 2 pi. So if we want to discuss its stability, we know that aromatic compounds are most stable. Least stable are anti-aromatic compounds, and non-aromatic compounds are as it is between those. Okay, so now let us discuss some of the abnormal cases. Means these are really mischievous cases, I can say, because these are non normal. So let us consider this molecule. We can easily see that there are two, there is loop current and there is resonance, and there are 4 electrons which are revolving around, and it fits into the category of anti-aromatic compounds. But since anti-aromatic compounds are least stable, the compound itself wants to convert into another form to get stabilized. So what it does is, two molecules come and they join. Two molecules come and they join. What happens is this pi bond gets broke into one electron here and one electron here, and similarly the another molecule also does this, and they get joined and they get non-aromatic. So that's why they get stable. Now here it is, there is this molecule. We can easily see that there are 8 electrons revolving around, and there is resonance, there is aromaticity, and these are anti-aromatic. But what it does is it converts its shape into bot form. By this, what it does is it gets non-planar, and we know that non-planar structure cannot do resonance. So if it does not do resonance, then this will not show aromaticity, and this will convert from anti-aromatic to non-aromatic, which is more stable. Okay, our last example is this aniline structure. Now we can easily count that there are 10 electrons, and this fits into the category of aromatic compounds according to the rule 4n plus 2 pi. And if we replace n equal to 2, then 4 into 2 plus 2 equal to 10 electrons. So this must be aromatic. But if we analyze its structure, there are two hydrogens which are very close to each other. These are so close that these do steric repulsion, and again the molecule gets non-planar. So if the molecule is non-planar, then there will be no resonance, and this will not show aromaticity. So ultimately, not every time the molecule will be get benefited. There are some compulsions for it to get converted from aromatic to non-aromatic. In these cases, the compounds was getting stabilized, but in this mischievous case, the compound is actually is in disadvantage. So this was it for resonance.